This is the PCB tutorial for DipTrace, and the presentation I made it a very long time ago, but I still think it's relevant, and I didn't have the time to complete update it, and I think the most thing I like to update is probably just the logo, so it's like more just a formality of updating it, so there's not much real thing in there. So what will be covered today? What is a PCB? And what's the like the PCB layers and the terminology that comes with it, and how we're going to design a PCB using DipTrace, and some of the component marking conventions, and some of the common component package that we're going to use commonly. And at the end, we're going to make a demo of making a new component, and that will be the whole topic we'll cover by this tutorial. And so what will be covered in part 2 is the schematic editor and the layout editor. That's how you actually make a PCB. The previous part is how you make a part that you're going to use for all these the next step. So the date is wrong, but yeah, that'll be tomorrow, but yeah. So what is a PCB? PCB is a printed circuit board, so that mechanical support and electrically conduct component using a conductive trace, and pad and other features etched from a copper sheet laminated into a non-conductive substrate. PCB can be single layered, so it has one side only. Double layered has two sides, or multiple layers when it stack multiple layers of coppers, insulation, copper insulation, copper insulation, and use vias to pass the signal through. So PCB allows miniaturization and mass production electronics, which is basically present in all the electronic device and appliance that you're going to encounter today. And at Migo Robotic, we design our own PCB. Probably you're going to encounter double-sided PCB. I recommend it to you to not try for layered, which is possible, but rather it's very difficult to manage from a beginner perspective. All right. So let's go for PCB layers. The PCB usually, if it's a two-layer PCB, then it usually have these features that you can use. So top silk screen, which is a layer that you use to make some sort of component markings and make like some labels or even artwork if you wish. Top mask layer, that's a layer that covers all the coppers such that when the PCB is still exposed, the trace of the PCB will not be exposed to the element or conduct when something fell to it short of the pin from each other. The substrate is the non-conductive things that it's in between PCB. In between the copper layers, such that well, it doesn't conduct from top layer to the bottom layer, and the same layers happen again. So copper, mask, silk screen, and yeah. So these are the basic layer for PCB, and also there is a feature called a via and a through hole, meaning that this is a hole on the PCB that allows the top layer to connect with the bottom layer. Yeah, so silk screen, outermost layer used for labeling, component numbering, orientation indicator, and graphic. Usually white. I think if you order black PCB, it will be white. If you order white PCB, it will be black. And I think other colors. If our supplier for PCB is Electro, and the mask depending on the color of the PCB you're gonna order. So yeah, so this is a LED that is used to indicate the power, and there's a resistor that's 330 ohm, so that's marked by the 330 passing through, and yeah, and there's a graphic of the spark fan logo, which is one of the DIY manufacturer for all the components. And solder mask, so it's a non-conductive layer that does not bond to solder, so use it to electrically insulate and constrain solder flow. I think the flow, yeah. So you can see here, these are the green part is the mask, and the exposed part are not being solder masked, so they're exposed that you can solder the component to it.
Sorry, the dark green is the mask?
Yeah, the dark green is the mask. And so what this does, sorry, just gonna What it does is that this allows you to control where the solder will flow, because when the solder is melted, it will become a liquid, and as a liquid, it will just splatter everywhere. And the harder you get, the easier it is to flow. So with this, as the solder will not be able to bound to the mask, you'll be held together by surface tension, and thus be constrained by the pad itself. So yeah, so solder mask can be green, but it can be other colors. So SparkFan has red, Arduino has blue screen, and Migurobody sometimes printed, mostly printed in black, but you can choose a color when you order them. Yeah, so layer, copper. So it's a thin layer of copper foil laminated into substrate layer with heat and adhesive. So the copper layer thickness can vary, and it's specified by ounce, by weight, in ounce per square feet. And yeah, so exposed copper layer is usually coated with other metal alloy to help soldering. For example, double-sided PCB is and for double-sided PCB, copper is applied on both sides of the substrate, and they can connect it by using vias. So this is a very easy copper board that you can order from electronic stores, and you just cut it and you can solder a component to it. What I want to show is that the difference between, so this is what you usually see as a copper as a color, and this is what you see on the PCB. So you can see that there is actually a coating on top of this copper to make it more easy to solder, and to make it less corrosive, to make it more corrosive resistant. PCB layer substrate. So, well, substrate is made from fiberglass, and this layer is solid and give PCB rigidity and its thickness. Also, it acts like a dielectric that insulates copper layer. So it kind of looks like this color, and this one has most of the copper removed with no mask on it, so you can see what the substrate looks like. All right. Okay, PCB terminology, flux. So flux is a substance that is inert at room temperature, but which becomes strongly reducing or corrosive at higher temperature. So this prevents formation of metal oxide, which helps soldering to bond to macro surface. Not only sometimes the solder will not bond to a metal oxide surface, as well as the heat transfer of a metal oxide surface will be very hard to transfer the heat through that. So sometimes it's still called resin, and it comes into small box form, pin form, or embedded directly into the solder. So if you see that the solder has a small empty hole here, and which the flux resides. PCB terminology, pads. So it's what we call a pad is an exposed metal on the surface of the board, which component can be soldered onto. So the pad can be surface mount, like this one. So it is a surface mount pad, or through hole pad, which is just two pads on both sides and with a hole in the middle. Plain and pour. So it's a continuous block of copper on the PCB board defined by the border rather than by a pass. So if you see that this is what we call a trace, so that's a signal line that passes through one point to the other, while this is a pour, which is defined by the border rather than its pad. All right. Solder. So it's an alloy and substrate composed about two or more metal that has a really low melting point. So before it was lead and one other, it was very leaded, and I think some of the our solder is still leaded. So when after you solder something, it's very good for you to wash your hand, because you don't want to get lead poisoning, because that's really bad for you. So yeah, remember that. So it provides good electrical conductivity and mechanical strength. So it typically comes from a long wire or a spool of wire or tubes, and yeah. So sometimes we use different kind of solder, which is what we call paste, which is, as the name suggests, is some sort of paste that suspend all the solder in some sort of with the flux together, so that when you heat it up, the whole thing melts, and it's more used for surface mount components. And when we go there, I will cover that. So soldering, so which is the process of two metal item component PCB or wires. A wire and wires are joined together by melting and flowing the solder to the joint. So usually we use solder iron for this purpose, but we also has a handheld air gun that propel heated air that at 200 or 300 degrees Celsius. Surface mount components. So it's a construction method which allow component to be simply set on the board by solder, not require the lead to pass through the whole of the board. So you can see that this component, this capacitor, is soldered directly by this joint and this joint without needing for it to penetrate through the PCB. And that's basically surface mount. So how this works is just usually there is a mask layer, we call it the stencil, and we place the stencil onto the PCB and allow the paste to go through the stencil, and we heat up the whole PCB to and we put a component on and heat the whole PCB such that the paste melt and bound to all the component that was on it. A thermal, so it's a small trace to use a connect to a pad to a plane to resist the heat flow. So if a pad is not thermally relieved, it becomes very difficult to get the pad high enough temperature to create a good solder joint. So for a good solder joint, you will need both metal to be hot. Essentially, that the pad itself and the lead of the component has to be hot for you to properly solder something. So with a pad directly embedded into a plane, that becomes really difficult because as you know, the copper is the most heat conductive metal, one of the most heat conductive metals. So the heat will get redistributed across the board really quickly. So you want some sort of some sort of thermal, which is a small traces with empty spaces, allowing the heat to be or rather restricting the heat flow such that the pad can be very elevated temperature in a very quick time. Through hole. So the through hole is a hole on the board which component can be inserted and soldered. So for this resistor, you can see that the lead is inserted in between a hole, and that can be soldered directly, or a component that can be used for these holes, which means that this resistor is what we usually call a through hole resistor. PCB trace. So it's a continuous path on the circuit board. So as you can see, the RES has a trace coming from out of it and going down this way, and the 5 volt line have the trace going to the right. So the trace thickness is something you can choose, and depending how much current you're going to conduct, you choose the thickness of the trace, which we have. I think there's an online calculator for you to do that. A vial, so it's a small through hole that designated to pass a signal from one copper layer to the other. So this is a vial. As you can, the difference between a through hole and a via is usually via is coated by the mask layer such that it's not exposed for you to solder onto, versus the through hole is exposed. So yeah, so this is a summary of the PCB. So flux, pad, plane, solder, thermal, trace, through hole, wires. So just go over it because I had to be really explicit. So I want to make sure that when people not coming to the tutorial and just following the presentation will be able to get all the information they need. So PCB design process. What we usually do is we make a footprint, which is the physical layout of a component, and we attach that footprint to a symbolic representation of the chip into a symbol, and we insert that into the schematic of the we insert the component, the symbol of the component into the schematic, such that we make a circuit that actually might or might not work, and then we make a layout out of that schematic. So the first thing for you to do is of course have a clear understanding of what you want to achieve through this board, and how each individual board become each sub module of the schematic connect together and make the whole board serve its function. Yeah, so just go through here. So if you have a new component, then you have to create a new symbol to use it in the schematic, and add a new footprint to the new layout. I think the terminology for DipTrace is different. So the footprint is called a pattern, and the symbol is called a component. Yeah. So DipTrace, we use DipTrace to design our PCB. DipTrace is one of our sponsor, and I personally believe that is the most user-friendly PCB software out there. If you try to use Altium or Eagle, you'll have a really hard time. It's a very steep learning curve versus the DipTrace. And okay. So DipTrace editors. DipTrace has 4 editors. Schematic editors, a PCB layout, component editor, and the pattern editor. So today we're going to use the last 2 of them, and to make a new pattern, new component and a pattern library. Yeah. So common component footprint. Resistor, capacitor, we're going to use 603 and 805. So they're just common footprint names that might or might not actually make sense at all. So just that's something we usually use. And the integrated circuits, there's SOT, SOIC, SSOP, QFN, QFP. So it doesn't make sense at the moment, but SOT, SOIC, and SSOP are really similar chips. So you can see it. This is what SOP looks like on the PCB. This is SOIC, and if there, I don't know if there's a SOT. Yes, so there's a SOT package over here. So these are more having the lead on the side of the component that allow you to solder on the side. And QFN and QFP. QFN is more complicated, so it has no lead on the side, and you have a small pin you can solder to. And QFP is very similar to SOP, except that you have pin on outside of the chips. So they're just different form factors. And if you take some time to look into this PCB ruler, which tell you all the common footprint, you'll have a better understanding of all the common component size we use. Next step, component marking convention. So pin counts clockwise, and pin 1 should be indicated somehow. And polar components such as capacitor and diode should be clearly indicated. So for this chip, you can see that it has 8 pin. How do you know the first one? So the one with the U is where you starting counting the pin. So this will be 1, 2, 3, 4, 5, 6, 7, 8. So counterclockwise. And for this QFN package, you see that pin 1 is labeled with a dot, and also the end of the chip is labeled with a bar, so that you know that this is pin 1 and this is the last pin of the chip. Same thing for this QFP package, a dot, and then also a small marking on the inside of the chip to indicate that this is the end of the count. This is beginning and the end, essentially. And for this one, it will be difficult for you to do that because the inside of the chip is covered by a pad as well. So you just use this as an indicator for the pin 1. And for some of the more older version of components, such as through-hole, the first pin is indicated by a squared through-hole, and the rest of them are indicated by a rounded through-hole. So in that sense, that this is a pin 1, 2, 3, 1, 2, 3, 1, 2, 1, 2. And for a capacitor, for example, you can see that the positive terminal is labeled with a plus, and for diode, you see that cathode is labeled with some sort of band at the end. So make a component. So how to make a new component? You need to make a pattern first, footprint of the pattern of the layout. If for use later for the layout editor, if it does not exist in default library, because the default library has a lot of things already existing in it, so you can just use that without making your own. So then you have to make a symbol to use for schematic editor and attach pin of the symbol to the pad of the footprint. So in the past, I want to use a 555 timer as an example, but I think that defeats the purpose because the footprint of 555 actually already exists in the library. So I'm just going to use a different component. So so this time we're gonna use the depth sensor that's being used in UV, but we're gonna do that once we get there. So what is a data sheet? So a data sheet is a document that details the performance and the characteristics of a component. So typical data sheet including part numbers, name, available packages, device property, functional descriptions, pin connection, pinout diagrams, absolute minimum and maximum ratings, recommended operating range, application recommendation, and typical application, physical dimension, and packaging and the ordering information. So data sheet can be really short, like 2 pages for 400 and 200 different registers, or extremely long, like around 500 for a microcontroller, and they can go up to 1,000 pages if you combine all the documentation for a microcontroller together. But you should always find the information you need to use it. So, okay. So this is no longer relevant, and for this, so making the pattern. So mechanical drawing at the end of the data sheet is what you usually use to make a pattern, and the data sheet usually contains recommended footprint, but might omit it in the case that it's a standard footprint, so that you can find it in the library of the of DipTrace. Yeah. So if you should use the recommended footprint if it exists. If not, use Google to find another drawing and double check if the mechanical dimension actually match the one that found in your footprint. The unit uses footprint might be inches or millimeters, so make sure you are using the right unit before you start. I'm gonna close this one here, and let's look at the data sheet for the depth sensor first. So this is the depth sensor that AV used for measuring how deep it is in the water, and it has a resolution of up to 0.2 millibars, so you can very accurately know between a millimeter of the depths in water. And we actually designed our own board to use this. So because this footprint has a pad that's different from the rest of the pad, which is something I want to demonstrate, so this is why I'm using it. As you can see, there's a description of what it is, like what's the main feature of this sensor, what's its field application, functional block, and some of the technical data as a table. And if you go here, there are absolute ratings and some of the characteristics for the components. If you go further, how to use this as a system diagram, how it works, and how do you select each interface you're going to use, and how you communicate with the sensor in a more software oriented level, how you convert the data of the sensor from binary into actual temperature and pressure, and how do you actually interface with the chip electrically, all the information like that. And at the end, you have this pinout and configuration, so recommended pattern layout, and what's the physical dimension of this. And let's go for DipTrace. So let's go to the pattern editor. Yes. So this is the pattern editor, and yeah, there are many patterns already exist in the general library. As you can see, there are many of them, each one with a different pattern. So
sorry, what's a pattern again?
A pattern is a footprint that the layout of the or the footprint of the chip you're going to use. onto the PCB, so how it fit onto the PCB itself when the physical layout is there. Yeah. As you can see that this is a capacitor pattern, so you have two terminals of the capacitor, and this capacitor has an outline like with a marking with the green lines, so that when you put it on, it will solder to this pad and you'll fit this green line area sort of thing. And yeah, so this will be a chip, and that looks like this, so it gets fit like that, and the orientation indicated by the U shape at the top. Yeah, so very similar to that. So the first step is to create a new library. So I'm just going to do this. No, do I want? So the name of the library will be called the MS5803. I'm just going to copy paste that. And yeah, so choose it to save it onto user library, which is where you user pattern, which is where you store your own stuffs. Okay, I'm gonna click OK, and now that is created, let's first put all the information you needed. So the name of the pattern is MS5803. Reference design is what you use. So give a package. So yeah. Sorry about this. Reference design. So put it. It's short for ref design. Is a standard made IEEE. So it's used to ambiguously define a component on a schematic or layout, so that you can say, for example, this resistor is U3, something like that, so that you can know, you can identify all the component without needing to point to that resistor, saying that resistor I'm talking about. So for all the chip you're gonna use, probably gonna use U, which indicate a IC integrated circuit. So the ref design will be U, and the value leave it empty. Data sheet. So we're gonna just copy paste the link from my history. Over there. So let's go look at the data sheet. This component has 8 pads, and one of the pad is a different shape than the rest of them. So just gonna check what's next. Yeah. So the first thing first is that we want to make the pad for all the pads that are the same. So use that as a default pad layout for all of them. To do that, we do go to pad property, and because all the pads are surface, so we leave the type as surface, but you can go to through hole if you wish, and that will change accordingly. So surface. Shape of the pad can be ellipse, oval, rectangular, or polygon. So polygon is used when you have really weird pad shape that's not covered by all those things. So you can define your own geometry for the pad and use that for a pattern. And the next thing we need to put into is the information of the width and the height. So the width is from this data sheet is 2.5 millimeters and 2.25 millimeters, and the height is 0.8 millimeters. So right now we are already in millimeters, but if you want to change to inches, you can go to a view display view unit, and you can change it from inches to mil, which is 1,000 of inches, and millimeters. So part property, we said the width is 0.9 and the height is 2.25. So that changes all the pads we're gonna use. So let me just put some few pads down there to have a look of what it means. So if I change the pad property, then all the pads that's in the default layout will be changed to that value. For example, if I change 2.5, you can see that it gets longer, and if I change to 1, it gets really short. So let's go back to the original value, and we would need 8 of them. So let me just put 8 pads together. Okay, and so you can use space to rotate the pads. such that it will be sometimes it will be easier to do for you to make it this way. So we're gonna try to arrange them together, and let's go back to the data sheet to see the measurements that we have to take. So from the pad to pad spacing is 5.35 millimeter. So just do that. 5.35 divided by 2 is 2.675. Just copy that. So we know that the y direction, or rather the x direction is this, and let's just leave the y direction 0 for now. So then you have to use a dimension. You have to use another dimension. So the distance. So it's always preferred for you to have the footprint to perfectly centered through the axis, such that it will be, when you rotate the footprint, it will be rotating around the center of the footprint rather than jumping randomly. So for example, if you put your pattern somewhere here, when you rotate on your schema on your layout, it will rotate around this point, so it gets really weird. It will rotate different quadrants. So it's recommended for you to put it on the right place. So the x is minus that, and the y is 2.25 plus 1.3 divided by 2, so 1.9. So 2.25 plus half of 1.3, so 1.9. That's our first pin. The second pin will be the same thing for the y, 2.75, and for the same thing for the x, and for the y it will be 1.3 divided by 2, which is 0.6265, 0.65. And we do the same thing for pin 3, which is exactly the reverse of, well, negative of that. And pin 4. Okay, that's our first 4-pin in place. And the next step is to put the 5. So as we mentioned before, we go into a U shape or counterclockwise counting. So the pin 5 will be here, and just put it in 2.675 minus 1.9 6, 2.675 0.65, and 8 is 2. Now, pin 7 is different than the rest of the pin. If you look at the data sheet, pin 7 is slightly longer than the rest of the pin, so we're gonna have to treat it differently. And let's just do that. So for you to have a pin with a different pattern, you're gonna double click on the pin itself and go to type and dimension and uncheck use patterns pad property. So you uncheck that, and you have the similar dialog as the pattern property, but this one will only affect this pad in particular. So the thing that we have to change is the height of the component from 2.25 to 2.8. Okay, and we have to put it in place, but for now, we can set its y coordinate really easily because it's the same thing, so 0.65. And for its x coordinate, it will be slightly more difficult because we want to make sure that so this is a measure tool. We can measure the distance between two things. We want to make sure this edge and that edge is exactly the same, and yeah, so we already knew that what this is, so I can just calculate by hand, but I rather calculate the position. So what we do is do a rather simple geometry that you can calculate. Okay, close the thing. So the midpoint of this is 5.365 divided by 2, and that is where the center is. And our chip is our chip have the our chip has 2.8 onto that, and we divide this whole thing by 2. I believe that is the center where it should be. So it will be at 2.7375. No, I did my math wrong.
Why can't you just switch to the left and then just use the align thing?
Yeah, so
Right here it's 0.6.
so this is very hard to position, right? And because the unit displayed here is actually not the exact unit, so it might be different. We can do that.
Not exact?
No, it's not exact. So it might be exact in some of the case. It might not be exact for this case.
So it's not a reliable tool to use.
It's not a reliable tool because it only show you two significant figure, but relatively it should be good enough for most of the case. But just keeping that in mind. Sorry. Oh, so you use this tool, so the place pad, and you can use place pad lines such that you create a line of things, or you can create a square pattern as well. So you can create multiple pad like that, and yeah, and even circular pads. Okay, so this is the basic recommended layout for that, but we need to add some sort of marking indicating what's the dimension of this. So let's do that. So this chip will be 6.4 millimeter wide. So just gonna add a line going from 3.2 to 3.2. The height of the chip is 6.2, so the y-axis is 3.1 and 1. So the reason I'm doing this instead of using the rectangular tool is that you cannot have it's preferred to not have the silk directly onto the pad, such that when you manufacturing this, the silk will be cut off from the pad. So yeah. I'm gonna do the same thing for here.
So what are you trying to do now?
Making a component marking for the component such that indicate the dimension and where is the first pin of the component. So with that said, usually I deduct this by a little bit, such that because this chip has a geometry of a chamfered corner, so we can indicate that by deduct this by 2. Actually, I did something wrong. So this step is more artistic rather than functional, such that to indicate where those things are. So for the horizontal bar, I'm gonna draw them out first, but I'm gonna draw them on the assembly layer. So which is the top, which is ASCII layer, which will not be printed onto actual PCB. So I'll just draw it like that. As you can see, it's gray, so indicating that it's ASCII layer. So I'm gonna move this to So the X will be 3.8.
So the gray and the green lines are two different materials, correct?
Rather, it's the two different layers.
Two different layers.
Yeah, in the sense that this layer will not be printed onto the PCB, and the other one will.
The green will and the gray will.
No, yeah, that's exactly.
So they're just to help you all the time.
Yeah. So, oh, wait. So the gray line is to help you to indicate what's the physical or what's the construction, some of the construction you put into to create this component, and the green one is the one that will get printed onto the board to indicating where and how the board is oriented, and what's the physical dimension that just indicate that this is a component, because sometimes like you have a lot of things crammed into a very short area, so you'll be better for you to know which one is what. Click on 2. Okay, I think the chamfer is a little bit bigger than I expected. And so 3.1 minus 2, so 6. And now I can change the grid to 0.1 millimeter and try to draw a line from there to there. So now I'm going to draw on the circle layer a line from here to here. Okay, and so that is most of the marking for this chip. The last one is a dot on the pin 1, so just use the rectangular tool, the circular tool, just draw a dot.
But what does adding the corners add to this thing? Like before it was just square, but why did you add the...
Because that is what the chip is, right?
Oh, it's specifying that.
Yeah, so it specified that this corner is chamfered, it has a edge. So usually you don't care about this, you can make this square, but I personally prefer that you have a full understanding of the chip. So
But
yeah.
like what would adding a chamfered edge to it add? Like, why would they specify that instead of just like the square rectangle?
Because that is what the physical chip is. So I don't know why they decided that this has to be chamfered, and yeah.
You're just following.
I'm just following it, but if you want to make it a square, so I don't think the space saving of this will be enough. Rather that when you solder this on, there will be a square versus the chamfer that already exists on the chip. So there might be a discrepancy that I usually try to avoid. So yeah, so the last thing we add a dot to this, and we can see how this chip, how this pattern looks like in 3D space. Yeah. So I think that is the last thing we want to do. We want to verify and all the dimensions are exactly the same as specified in the datasheet. So we use the measure tool. Usually, so you have a different tool for horizontal, vertical, and free and like radius measurement. So horizontal and vertical is the most one we use. And let's just measure the things. So horizontally, we want to make sure that this and that is 1.5.35, and so this is the only horizontal dimension constrained by the datasheet. Oh, no. Okay. And yeah, so 5.35. So I specified that, and then we can also measure the path distance, but we set that correctly, so it should be the same. So I'm just going to do that. 5.25 for this one, and 5.8, the 2.8 for this one. And then we can measure the vertical distance from this to that. It will be 1.3, and from here to here will be 1.25. Same thing for here. So this step allows you to see that if your footprint matches exactly the one depicted in the pattern layout. Right? And I guess one last thing I'm missing is the vertical distance of the pad. So 1.9. So that you know that your layout is exactly a replica of this thing by measuring all this measurement. And these measurements will not be printed onto the final board, so you can be free to add them as you wish. Just make them clear and easy to understand. Let's put it on right here. All right. So this concludes the first part of this. So I'm gonna save this onto a different folder. There are naming conventions for components, so usually it goes by the component part number. So MS 385803, all lowercase, separated by a dash. The company name, which is measurement. When you need to insert a space or any other character, replace it with an underscore. So it will be measurement specialty. And the dash, the last one is a short description what it already is. So just pressure sensor. So this concludes the first part of the tutorial. No, well, actually, first part of this. This concludes the part for the pattern. Now we're gonna move into component editor. So I'm gonna close this and go to component editor. So component editor already have many components, and you can see that there's a preview of the pattern attached to the component, and this will help you to visualize what exactly component you use. So the first thing first, we're still gonna create a new library, and it will be still called the MS5803, and hint is it's up to you if you want to add it or not. So we usually don't care about that. So creating this new component, and so let's look at the datasheet again. The datasheet indicate what exactly the which pin does what. So pin 1 is 0 clock, pin 2 is ground, pin 3 is chip select, pin 4 is not connecting anything, pin 5 is VDD, and pin 6 is protocol select. Pin 7 is data 0 pin in and 0 pin out. Okay, so let's just do that. So very similarly, we're gonna place all the pins together. So just zoom in. One other thing I want to mention is that always use 0.05 inches grid for this application, and try to keep a 0.1 inch spacing between the pins. So just gonna drag and move all the pins together relatively. 5, 6.
How do you rotate it?
Space. So like that, and we'll try to move it to the center of the schematic for the same reason. And for usually, so you see the pin numbering is marked on top of the pin, but we want to show what pin each pin has what function. So we select all the pin, go to pin property, and check show name. So it will show 1, 2, 3, 4, 5, 6, 7, 8. So that's not really what we want, but we can change it later. So
how much is the distance between the two?
That has no bearing in whatsoever into the physical layout. So use as much space as you need it, but don't use too much space.
Okay.
So I'm just drag this on the side and this one on this side, so to see better. Right now, so pin 1 is SCLK, pin 2 is ground, pin 3 is CSB, pin 4 is not collect, pin 5 is B, pin 6 is pin 7 SDI, SDA, pin 8 is SDO. And as you can see, the overlap, so we'll just move further away from each other until like it actually fits. Okay, and then I'm gonna draw the body box for this component, something like this.
What does that mean?
Such that you have it's a box in the sense that it's not just pin floating around. Yeah, I guess this answer is kind of arbitrary, but yeah. So last thing, so most of the thing is so we already follow all the pinouts. So it's like this. Sometimes you might want to group pins together in a more elaborate fashion. For example, if you want to put a VDD with ground because they're both like power pins, and NC can probably delete them completely, and because it's not connecting anything, so you probably don't need to connect anything, right? And yeah, so PS and just something like that, so you can group the pin together rather than follow the pin out, follow the U-shape, the pin out for the chip, but just make sure that actual pin out of each pin actually like matches exactly what you expect on the data sheet. So yeah. So this will be equally valid as a component.
What do you gain by changing?
It becomes so for this chip, not much. But if you're looking at something like something like a microcontroller that has more than 100 pins, that it will be better for you to group pins by its function rather than go for the numbering. And that if you go for the function, you'll make your schematic better. But if you go for the physical layout, then you have some small insight into how you can implement the physical layout when you're doing the PCB. So yeah, there are trade-offs.
So it doesn't have to be clockwise anymore.
Doesn't have to be clockwise anymore, because this is not, because the schematic, the component, which is the symbolic representation of the footprint, has no physical bearing onto
so the previous one for the pattern we were doing.
Yeah.
That has to be
exact.
It has to be order 1 to 8.
Yeah.
This one does not matter.
This one does not matter. Yeah. And now we fill in the information. So the name of chip is of course MS 5803. 5803. Ref design still U. Value still empty. Manufacturer is measurement specialties. The link for the data sheet is at the. So have we not good one now? So go back to this again. Copy paste that. I highly recommend. I highly recommend it for you to indicate the data sheet for the chip, because it will be very easy for you when you do the design to just double click on the data sheet, and it bring you up the data sheet that you can look into, and you're gonna look into quite a bit. So the last thing you do is attach the pattern to the symbol by click on the pattern, and as you see that now it has no pattern. So we are going to find our pattern in user patterns, and MS. This is the last one we made. So you can see that because we ordered the pin correctly, the all the pin will be attached to the correct pattern.
So it's all automatic.
Yeah. So most of the time you automatic because the pin number and the pin number on the chip and the pin number on the footprint, well, pin number on the component and the pin number on the pattern is exactly the same.
Now hold on. If you left it as you know, because you reordered it,
Yeah.
right? Then you'd have to.
Or rather, because even though I reordered it, the pin number itself is still matching.
Okay.
So, for example, if I reordered, the VDD will still be 5.
Right.
So it will be still attached to the pin 5.
Yeah. Okay.
So yeah, and for some time that if you have a connector that has attached to a something that has was not designed for it, for example, I just click OK to say yes. For example, if your connector has a different naming scheme, sometimes if you have a big row of connector, it might not be used because if you have a grid of connector, it might not be U-shaped because you can't actually make a U out of a whole grid, like a square grid of connector. So it goes like 1, 2, 3, 4, A 1, 2, 3, 4, B 1, 2, 3, 4, C 1, 2, 3, 4, D 1, 2, 3, 4, and then if you want to connect that to something, so the pin number might not match exactly to the pin of the pattern. So in that case, you can click on it and drag and attach a different one, for example, like that. So now that my SCLK is attached to pin 2, and I can do pin 1 attached to that. So I essentially flip the ground and I attach the ground to the first pad, and the clock attach the clock to the second pin. But yeah. So I think the same thing, we have to save this. So I'm just gonna save it. Same thing MS. So same information. Part number, manufacturer. Okay, and so these are the footprint and pattern we made. So yeah, so this is basically what I want to cover. Do you guys have any question? Okay, one last thing I want to add is that when you use a component made by the other people, you have to click on here, this component thing, and go to library setup, and then you can add a folder or add a library directly, and that will be all showed up in the appropriate column of your um, of the groups. You can select it too. All right. And yeah, so this is it. Yeah, yeah, this is that's half of our story.
Is there another follow-up meeting?
Yeah, so there will be another one covering the schematic and the layout, but you can try to get your hand dirty with some random component you can find. Do you want me to just find a random sheet for you and to just practice?
Why
not? One other thing I want to cover is that sometimes you'll see chips with four-sided components, just like the one I just showed you. So for quad chips, you have a chip like this, and in the past we have been making components as if that you have more pins on the as if you have more pins, you can just put pins on top of it like that, right? So this is not recommended because this makes your schematic really hard to make and really hard to read. So if you have a chip with 4-sided, you cut in between, and this will be your first side, and then the second half will be the second side, such that you convert it into two-sided component in your when you're making a component. Just, sorry, what do you mean by that? What do you mean by that?
Well, you said like instead of doing it 4-sided.
Yeah.
Right, you'll do 2 of those and connect them together.
Yeah, so
Right.
it just do 1, 2, 3, 4, 5, 6, 7, 8, 8 like 10,
Yeah,
like
right.
just as if it's a one two-sided
Right.
chip split in the middle. So for example, if this, let's say you have a chip with, just do a quick example. This is a 4x4 chip, right?
Right.
And instead of doing this, you move 13 here, 14,
Okay.
14 here.
So just extend it.
Yeah, and 15 like that, and then you move the other side likewise. So 21 will be like this. So just keep doing that so that you shift the whole thing.
Are there any advantages to doing it 4-sided?
Yeah. Advantage of doing it 4-sided is more having an insight into making the layout while you're doing schematic is the same thing, but because of the chip gets really complicated, it makes your schematic not readable at all. So the advantage it's not enough to outweigh the disadvantage. All right. So.
So the point of like the component editor is mostly to name the pins, or?
Yeah. So essentially, I just put a random pin number and that random part number, and it actually shows up as a footprint. Yeah. So okay, this one has a really weird cutout onto it. I think this is an altimeter. 6. What's the one I'm looking for? 4. 2. The other thing? No, it's not the thing. 1. Yeah. Yeah, so it's very similar to the one we just made. There's some weird path thing like this, but rather like I think it should be able to deal with them. And like one side of it's a different shape than the other side, so the one pin is different than the other, and the pin numbering is different. So pin number starts 1 from here, which is kind of weird. And yeah. So I'm gonna link this to the workplace event, and if you can have a try of making it, if you want me to have a look at the end to give you some sort of feedback, so where are you gonna post the recording? The recording will be uploaded to YouTube. Oh, it's fine. And it will be shared on workplace as well. It is in pods. All right.